For this video, we will be talking about section 5.3, which is scatter plots and lines of fit. To start, we have some vocabulary here, actually quite a bit of vocab here. Our first vocab word is bivariate data. This consists of pairs of values. A scatter plot is a graph of bivariate data that consists of ordered pairs on a coordinate plane. Using a scatter plot can help you see the trend or the general pattern. A line of fit is used to describe the trend of the data in a scatter plot. We will talk a lot about lines of fit on the back side of your notes. And then the last two words we have here, linear extrapolation is the use of a linear equation to predict values that are outside of the range of data. And then linear interpolation is the use of a linear equation to predict values that are inside of the data range. And we will also talk about that more on the back side of your notes.
Next, we need to talk about the different types of correlations there are for scatter plots. So first we have a positive correlation. This is as x increases, y increases. So basically from left to right, what's happening is those dots or plot points are trending in an upward pattern from left to right. That's the biggest point here, is from left to right. A negative correlation, the points would be going down, generally speaking, from left to right. Again, they're not going to make a perfectly straight line. That's why it's called a scatter plot. However, if there's a general trend or pattern, it does have a correlation. Now you'll notice on this one for no correlation, there is no line that I could draw that would show a general shape of those points. So that's why this one would have no correlation. It says X and Y are not related at all. So looking at these examples for 1, 2, and 3, looking at number 1, landline telephones in the US, so years since 2000, and then how many landlines there are. If you don't know what a landline is, that's sorry, I got cut off. That is like a home phone, if any of you still have a home phone. Regardless, they are going away. People nowadays less and less have them. So if you notice right here, it is very, very gradual. But if I was to draw a line that would show the general shape or pattern of those points, this is going in a downward pattern. So this would have a negative correlation. Looking at number 2, this one's not labeled with anything, so we don't really have an X to compare to a Y, but these dots right here are all just kind of all over the place. So we would say that this one has no correlation. Something I do like to bring up that's a good example of something that has no correlation is like your age and your shoe size. Just because you're a certain age does not mean you have a certain shoe size. Those numbers could be all over the place. There's lots of examples of what a no correlation could be, but there's just one for you. And then the last one we have here is the New Orleans Saints 2014 roster, height in inches, and then the weight in pounds. Generally speaking, that is trending upward. Sorry, I got cut off again. Trending upward. So typically the taller you are, the more you weigh. Obviously, we know that there are some exceptions, and so that's why you'll see some of those points are a little bit farther from that line I drew. But typically speaking, that is trending in an upward pattern. So this would have a positive correlation. And that is it for the front side of your notes. We will continue on the back.
Okay, so now we have using a linear function to model data. We have some steps here to follow. Step 1 says make a scatter plot. Well, on number 1, they actually made the scatter plot for you. On step 2, it says draw a line. However, in this example, we really don't have to draw a line because they didn't tell us to. You'll see on number 2, they actually do tell us to draw a line of fit. So you really only have to draw one if they ask you to. So we're going to go ahead and move on to step 3 here on number 1. It says use the data points 10, 20, and 50, 80 to write an equation of the line of fit in slope-intercept form. So just to put this into perspective for you, we need a line that goes through 10, 20, and 50, 80. So that would be the line that we are writing the equation for. And again, you don't need to draw this line, but it's just to give you a visual as to what we're doing right now. So first things first, this is hopefully just a good review for you. Using those 2 points, we need to find the slope first. So 80 minus 20 over 50 minus 10. This would give us 60 over 40. So then we would get a slope of 3/2. If you simplify that all the way. So then I'm going to take one of the ordered pairs. I'm going to go ahead and go with the smaller numbers there. So y minus 20, put it in point slope form, equals 3/2 times x minus 10, and then start converting to slope intercept form. So distribute first, y minus 20 equals 3/2 x. 3 times negative 10 would give us negative 30, divided by 2 would be negative 15. And then we're going to add 20 to both sides. And when we do that, we get y equals 3/2 x plus 5 for our final answer here for writing the equation. Now, this says to predict the amount of milk needed for a 17-pound goat and a 55-pound goat. So, I guess I am just realizing that I never talked about what the scatter plot represented. So this is about a goat feeding based on the weight. They're trying to predict how many ounces a goat would need based off of its size. So the first thing we're going to do is start with the 17-pound goat. So all I'm going to do is plug this in for x in my equation that I solved for. So I have y equals 3/2 times 17 plus 5. If you remember order of operations, you have to multiply 3/2 by 17 first. So we would get 25.5 and then have to add 5. So that answer would be 30.5. And since this is technically a word problem, there's labels here. We have to label our answer with ounces. So a 17-pound goat would require 30.5 ounces. If we were to look at the graph, 17 would be roughly right here. And if I followed that up to on my trend line, that would make sense that it's right above 30 right there. That would be an example of interpolation because it is inside all of your known data values. Now, 55-pound goat would be over here somewhere, and that's actually on the outside of your data. So this would be an example of extrapolation, just to kind of bring that back, those vocab words back in there for us. So we're going to go ahead and plug in 55 for x now. So y equals 3/2 times 55, and then plus 5. This would give us 82.5 when you multiply 3/2 by 55, and then add 5 to that. So we would get a final answer of 87.5 ounces. So that would be what a 55-pound goat would require. So notice that you have two answers here. Make sure you try to stay organized in your way of answering these two questions on part B.
Okay, so for our last example in our notes, number 5 says the table shows the average length in minutes of a professional baseball game in selected years. Part A says make a scatter plot and draw a line of fit. So you'll notice our graph over here on the right is very, very blank. So starting out by doing that, I notice when I go to graph this first ordered pair of 2005 and then 169, when I go to look at my y-axis, it skips a tick mark every time. I do think it is more helpful to have all of those numbers filled out. So I'm going to go ahead and fill in the numbers here. When I look at 165 to 171, that counts by 6. So then half of that would be counting by 3. So then this is going to actually be 168 here. This is going to be 174, 180, 186. And then this is going to be 192. I do think that is a lot more helpful when we go to actually graph these points. So then, and I'm going to erase this because I don't want anybody to think that we needed to circle that for any reason. I was just trying to point out where I was at. 2005, 169 would be 05, and then just slightly above 168. 2007, and then 175. 05 to 09, 2007 would be right here. If you want to label those, you are also more than welcome to. Actually, let's just go ahead. 11, 15, this would be 19, and then this would be 23, just in case we need it. So then 2007, 175 would be just slightly higher than the 174. 2009, 175 would be the same height. And then 2011, 176 would be just slightly below the 177 mark. And then let's see, 2013 and then 184 would be just above the 183. 2015 and then 180 would be right where those two lines intersect, and then 2017 and 189 would be that point right there. So there's our scatter plot. All of our dots are ordered pairs on the graph, but now it says we have to draw a line of fit. So I'm going to get my ruler out here. Maybe. There it is. Okay, when we draw our line of fit, they didn't tell us what 2 points to use, like number 4 did, right? Number 4 told us to use 10 and 20, or sorry, 10, 20, and then 50, 80 to write an equation of the line. Well, they're not telling us that here, so we have to actually figure out what would be a good line of fit. So something that I would like to point out to you is if I picked these 2 points right here, and I drew a line through those 2 points, and I called that good and said that that was my line of fit. This would be an extremely bad line of fit because my line of fit goes higher than the rest of the points that are not actually on the line. So you'll notice the 2 that I picked, obviously it goes through those 2, but then it actually goes through a third one. Then I have 4 points that are below the line. This would not be a good line of fit. Now, on the other side of that, if I picked, say, these 2, for example, to draw a line of fit here, fix my ruler, draw my line. This only goes through 2 points, and then the rest of the points are above the line. So these are both examples of lines that are not good lines of fit here. I'm looking for a line that goes through the middle of the data, touches as many as possible, but then has an even amount of points above the line and below the line. So I am going to erase the orange and the blue. And then if I line my ruler up, let's see, I'm just going to kind of test my ruler here. I think I like this right here. So I'm going to pick these 2 points right here. Okay, I picked this point and this point right here. So looking at my graph, when I drew this line right here, I see that it goes through the 2 points I circled. It almost barely touches this first point right here on the graph that we put. But then I have 2 other points that are above the line and 2 points that are below the line. Technically speaking, I have 3 above the line if we count the one that's really, really close to touching it, and then 2 below. So I would say this is a much better, accurate representation of the graph where we have an even amount of points above and below the line. It's just a better, again, the reason it's called a line of fit is because it's supposed to best fit your data. So now that we've chosen those 2 points, these 2 right here, we then need to fill out the blank about when it says use the data points blank and blank to write an equation of the line of slope in slope-intercept form where x is the number of years since 2005. This is actually going to throw kind of a wrench, if you will, in just flat out using the ordered pairs as they give them to us. Because they say right here x is the number of years since 2005. That actually means that 2005 is when x is 0. So with that in mind, we have to then figure out what is x when it's 2009 and what is x when it's 2017. So if we're looking at 2009, that would mean that x has to be, it would be 4 years after 2005, so then x would be 4. And then we have 2017 would mean that x has to be, so if 0 is 2005, 2017 is 12 years after 2005, so that means x would have to be 12 here. So instead of using 2009, we're going to use 4, and instead of using 2017, we're going to use 12. So then my ordered pairs are actually 4, 175, and then this would be 12, 189. So that it is something you have to pay attention to. We also have to round to the nearest hundredth, which we'll talk about that when that comes up. So now that we have our ordered pairs, it is now just like what we did on number 4. So first things first, in order to put it in slope-intercept form, we have to know the slope. So m equals, there's my 2 ordered pairs up there. So this would be 189 minus 175 all over 12 minus 4. My top number would become 14. My bottom number would become 8. And actually, I think I'm going to rewrite that right here instead. So 14 over 8. And then if we go to divide those, we get m equals, this would be 1.75. The directions say to round to the nearest hundredth. However, this is already rounded to the, I mean, it's not rounded. The answer is already in the hundredths place, so we know that we're good here. But if we had a number over here, this would tell the 5 what to do, whether it rounds up or stays the same. But since there is no number there, we don't have to actually round this one. So there's our slope, and then picking one of the 2 points, it doesn't matter which one we pick, I'll go with this one. So we have point slope form, y minus 175 equals 1.75 times x minus 4. And then from here we would distribute. So now we're just converting to slope intercept form. So then y minus 175 equals, this would be 1.75x, and then 1.75 times negative 4 would be negative 7. And then if we add 175 to both sides, that then puts y equals 1.75x, and then we would get plus 168 here. Now, something I do want to also point out, so we talked about how we can check our graph here with our slope-intercept form. If we pay attention to the fact that 168 is supposed to be our y-intercept, that would be this point right here. I would say we're a little off of that, but again, remember, we graphed this by hand. There's a lot of human error that can take place. So to me, 168 is definitely close enough to where I would guess that mine probably was at 164. But again, that is a human graph that was made. We are approximating things, so we should be in a ballpark of where that y-intercept actually lands on that graph. So this is our answer in slope-intercept form. And then we have part C, what was the approximate length of a Major League Baseball game in 2021? Again, remember, we do have to pay attention to the fact that X is 0 when it's 2005. So then what we really could do is take 2021 minus 2005. That would be 16. So then therefore we are plugging in 16 for X to find this one. So then, and actually I'm going to scroll down here just a hair, or maybe a lot. Okay, so then if I'm plugging 16 in for X, because again, that would be what X is with 2021 being the year that we're testing. So Y equals, this would be 175. We are plugging in 16 for X plus 168. This would give us Y equals, if you type the whole thing in your calculator or do it step by step, multiply by 16, and then add the 168, we would get 196 minutes. Again, with it being a word problem, we do have to label our answer. There we go. And that is it for your notes.